Okay, so today we have Sebastian Franco. Tell us about 2D 0.1 gauge theories, spin 7 Orientifolds and Triality. Take it away.
Okay, thank you very much. First of all, let me thank everyone for the invitation. It's good to be talking in the Quiver Meeting. It's good to be talking to so many friends. Today, I want to talk about theories in 2 dimensions with very little supersymmetry and 2D 0.1 gauge theories and their connection to spin 7 Orientifolds and how that explains triality and so on. So I want to provide the geometric realization of these gauge theories. This is based on work with Ángel Uranga, who's of course he's here. He's of course a wonderful collaborator, but also 2 rather extraordinary young collaborators, Alessandro Mirinio, who is now in Hamburg, and Xinyan Yu, who is my student, even though he's from NYU. I usually watch these Quiver meetings, and quite often they start with a disclaimer that they're not going to show any quiver. I will take that box, so you can remain here, no problem. You will see quivers in this talk. So let me see. Very. So
sorry, Sebastian, your microphone is a little bit. There's some other noises. Is it plugged in? Well, I don't know. Let's not. It's also fine. I mean, it's not too bad.
You let me know. Okay. So, I will. This is the outline of my talk. I will begin with some introduction and motivation of why we want to do what we want to do. In order to set up the stage, I will talk first about how to engineer 2D 0.2 theories using D1 branes and singularities, which is a similar setup and also related to the construction that we have. I will talk briefly about brane brick models, which are analogs of brane tilings for that situation. Then, for those of you that don't know so much, I will just refresh your mind about 2-dimensional 0.1 theories. And then I will introduce our construction of them, which is going to be related to some spin 7 codes. I will give you examples, and then I will tell you how, if time permits, how that construction gives a nice perspective, I think, on the recently discovered triality that these theories have. So I think that I don't have to say this in this audience. There's continuous progress in our understanding of quantum field theory, even if we use it as a common language for things going from particle physics to condensed matter physics. There are a lot of new tools and things that we continue learning on a daily basis. We have bootstrap, we have geometric engineering of gauge theories, we have things without Lagrangians, we have integrability, we have new approaches to scattering amplitudes and so on. So we continue making progress. And I think that it resonates with everyone that engineering quantum field theories in terms of string or in theory of D-branes is a powerful approach, sometimes for discovering new phenomena, other times, but also related to that, to getting some alternative perspective on something that one knows, right? So you get a different point of view. That different point of view might be in some sense simpler, and it might lead to some interesting extensions and generalizations. So today, I want to study 2-dimensional theories with 0.1 supersymmetry, really minimal supersymmetry. It's a natural step if you are following the sequence of, let's first study 2-dimensional theories with, let's say, 2.2 supersymmetry, then 0.2 supersymmetry, and then 0.1, because it's always natural to reduce the amount of supersymmetry and see what you can say. It's very minimal amount of supersymmetry, so there's interesting dynamics. There can be dynamical supersymmetry breaking, different space structures, interesting inertial flows, and so on. These theories are supersymmetry, but there's no holomorphy, which is something rather interesting. And there have been some people revisited this theories recently. I will review some of the things that they said, and they use some protective quantities, anomalies, elliptic genus, For example, they discovered that these theories have.
Can you actually change your microphone to the microphone on your computer? Because I think you're getting a lot of
Can you hear me like this?
noise, and we can really not hear you very well.
This is better.
Better? Okay.
This is better.
Very well. So good. And one of the nice things that people, Rukova and collaborators discovered recently was that these theories postulated that they obey a new infrared equivalence similar to cyber duality, if you want. I will explain to you in what sense it is similar, but in its simplest incarnation, you have 3 super QCD-like theories, or 2-dimensional 0.1 super QCD-like theories that flow to the same infrared physics. Okay, so it's of order 3. It connects 3 theories. And already in those papers, which were interested, by Kukova and company, in which they were interested in looking at this triality, they observed, let me move this thing to the side, very good. They observed that the theories that they seem to participate in this new triality, perhaps not surprisingly, but it's an observation, and according to Google, they couldn't explain much more on that. The theories that participate in the trialities look like real slices of their complex 0.2 counterparts. Okay, it looks like, you will see, I will show you, it looks like there's some simple quotient of the theory that relates them. Okay, so that already brings to your mind whether there is some deeper meaning of that quotient, whether you can understand it in the, geometrically or in more generality. So this is part of the motivation. We want to engineer these things on the work volume of D1 brains on singularities. So what the kind of picture that we have in mind, and this is, I always say it's a cartoon, it doesn't mean that you have to strictly interpret the directions in which these things are spanning. So you will have some D1 brains with a 2-dimensional work volume in which we are going to realize our gauge theory. We are going to probe, in this case, spin 7 holonomy cone. This will break 1/16 of the supercharges. This will break another half, and you will end up with the 2-dimensional 0.1 theory in the work volume. And we want to study this setup. Many of us in this meeting today have studied similar things, and we want to do all the things that we normally do. We want to develop the map between geometry and gauge theory, both directions, understanding in more detail. Hopefully, this construction will provide a geometric understanding of this observation of the real slice connecting the 2 types of theories. And hopefully also we are going to get the D-brain perspective on the 2-dimensional 0.1 triality. Right? If this triality is there, probably it shows in our construction in some way. Of course, I don't have to review this here, but we have done one typical or prototypical example in which this program was carried out at length, was in the case in which we were studying these 3 brains probing Calabi-Yau threefolds. We did that. We were interested, or you're interested in these things for many reasons. Might be applications to ADS-CFT, might be local model building, because you get 4-dimensional theories here. But it turned out, and it's a very rich story, which many people in the audience made very important contributions. But the infinite family of 4-dimensional n=1 superconformal field theories on the D3 brains, in the case in which you are probing a toric Calabi-Yau threefold, are described by brain tilings, which are things like this thing on the right. And the brain tiling, which it's a bipartite graph. I mean, at least what I'm representing here looks like a bipartite graph. Bipartite means that you have 2 types of, it's like a crystal with 2 types of atoms, in which atoms of type white are only connected to type black atoms, and black atoms are only connected to white atoms. And the interesting thing is that this picture here is really a cartoon of a physical brain configuration consisting on some NS5 brane, from which you suspend D5 branes, which are on the screen. Okay, so you can think about it as some two-dimensional version of a Hanani-Witten setup. And the interesting thing about this object is that it's a missing link, or is sitting somewhere in between the Calabi-Yau threefold and the gauge theory and the D3 branes, in the sense that it's easy both to read the gauge theory from here and the geometry from here. Okay, so both things are relatively simple, and this has simplified our task quite a lot. We can think about these two configurations as related by T-duality. Okay, and like the skeleton or the NS5 brane is a translation of the geometry, and the D3 branes become the D5 branes that are suspended from the D3 branes. Okay, so what we want to do, or what we first wanted to do, was extend these things to theories in 2 dimensions. First with 0,2 supersymmetry, that would be the analog of n equals to 1, and then we continue the story a little bit further. Okay, so as a starting point, because it's going to be a part in our construction, it's also a logical step to discuss it first. Let me tell you about branes and 2-dimensional 0,2 gauge theories. There are many ways of constructing these gauge theories. I will provide just one of them. So first of all, these theories are interesting for many reasons. The theoretic string, they appear in flux tubes or in domain walls in supersymmetric theories, depending on what the amount of supersymmetry that you have is. So we would like to study them. And over the past years, now it's several years, there were a lot of developments, interesting developments on the field theory side, right? Because you have chirality, holomorphy, and anomalies that you can use to your advantage. So, of course, this has been studied in the general paradigm of connecting these theories to higher dimensional theories. The energy flows have been studied in more detail. Things like that were similar to A maximization in 4 dimensions have been introduced. And there was a new triality, a new infrared equivalence that these theories have. So there are many nice field theory results, and we would like to engineer these things in gauge theory and see if we can say anything else, something new. Okay, so this was, for some reason, there's a B here, and we don't know. So there was the type of setup that we want to use is the setup that I'm discussing in all this talk, which is D branes in singularities. So, in this case would be D1 branes throwing Calabi-Yau 4 cones. We restrict it to the case of toric ones because they are sufficiently general, but they still have some properties that allow to say some, they have some special structures that are interesting. And it turns out that there is something very similar to the brane tilings, which looks as follows, right? So it's a configuration in this case in which you have D4 branes and an NS5 brane. They share 2 dimensions, which are the dimensions in which the gauge theory lives. Then, the D4 brane extends in 3 other directions. The NS5 brane wraps an additional 4 real dimensional space in here that I will be an holomorphic surface sigma. I will describe what sigma is shortly. And then the whole configuration is a point in the A9 plane, and rotations there correspond to the U1R symmetry. So what do we do with these coordinates, these 6 coordinates? We combine them in 3 complex directions in such a way that, let's say, the argument of them are 2, 4, and 6. So 2, 4, and 6 form a 3-dimensional torus. So what is sigma? sigma is the analog of what a similar thing would be in the brain tiling. It's the zero locus of the Newton polynomial. Okay, so you'd have your toric diagram, which have certain points. You introduce a monomial for each of these points, where the exponents are the positions in the three-dimensional lattice, and they come with complex coefficients. Some of them can be absorbed, some of them cannot be absorbed, and their meaning is very interesting. What they do for this construction is very interesting. So you set this to 0, and you have something that is 4-dimensional, which is sigma. And that's what I would call a brain brick model. Okay. The supersymmetry that is preserved by this configuration is, as expected, 2-dimensional 0,2 supersymmetry. Very good. So I haven't shown you an example of this thing. You know, saying that you have a function of 3 complex variables equals to 0, visualizing that is complicated. We want something similar to the brain tiles, and indeed, most of, or a great part of the interesting information that these configurations have is captured by some tropical limit, if you want, the skeleton of that sigma. Not just that, but its projection on the T3. This is what we call the coamoeba projection. You take that surface, you project it on the arguments of the complex variables, you take the skeleton of that. That is some object in 3 dimensions, which we call sometimes we use interchangeably the word of brain brick model, we also call it the brain brick model. So why is this object interesting? It does the same things that the brain tilings do for you, but for these theories. It fully encodes the 2D gauge theory and allows the connection to geometry in simple terms. So let me just show you. By the way, I could give 1 or 2 talks just about this, but this is not the topic of this talk. So, you know, either you go with it or you ask the questions afterwards. You know, some things will look like, you know, I'm not explaining them in great detail because you know, this is just setting the stage for what I'm going to do next. Okay, so let me just say that, you know, the 2-dimensional 0,2 theories that come from toric labial fourfolds can be described in terms of periodic quivers, which now live on a 3-dimensional torus. 0,2 supersymmetry has, you know, vector multiplets, which are going to be the nodes. They have chiral multiplets, which are these black arrows, and they also have Fermi multiplets, which are the red things. And they're analogs, not of the superpotential, but of the F terms that I will call the J and E terms. And you have, you know, one set of them for every Fermi, for every one of these special red guys. So this periodic quiver, which I have not discussed, captures the entire gauge theory. You know, you can read the J and E terms, and you can read the quiver from it. And you can dualize this object, and it will give you something which is a tessellation of a 3-dimensional torus, which I show here, right? So you can think about this as this skeleton that I was talking about. So this, you know, thing that is made out of faces is what we will call the skeleton of the NS5 brain, if you want. Inside each of these bricks, there are D4 brains, which corresponds to your gauge groups. Then, you know, faces connecting between 2 nodes, between 2 of the gauge groups represent matter fields, which can be either chiral or Fermi. The Fermis are represented then by these red faces. And the edges here, in which a Fermi and several chirals connect, something like the pages of a book, represents a term, one of these J or E terms. And if you can think about that, some term in the superpotential, you know, with some abuse of language. Okay, very good. So that's basically what I just said. You know, inside you have D4 brains. This represents an NS5 brain. The inside of each of these bricks corresponds to a gauge group. there are some phases which are oriented to correspond to chiral fields in adjoint or bifundamental representation of the two bricks that are separated by them. Similarly for Fermis, and this corresponds to the J or E terms. It's a nice observation if you want. This I represented here. I didn't tell you what geometry this corresponds to. Also, I didn't give you the unit cell, but this truncated octahedra, this is a truncated octahedron, like two square pyramids on top of each other, in which you chop the corners, corresponds to C4, flat space, or if you have many of them, to Orientifolds of C4. You can understand this because the theory for C4 is just the dimensional reduction of n equals to 4 superjumbles to 2 dimensions. So you have 4 chirals in the adjoints and you have 3 Fermis. And you see that each of these bricks have 8 faces, which corresponds to the 8 chiral faces, which corresponds to the 8 endpoints of those 4 chiral adjoints. And you have 6 Fermi faces, which, if you're considering a single block, are all the 6 endpoints of the 3 adjoint Fermis. The nice thing is that this is the truncated octahedron is the associahedron, so the permutahedron in 3 dimensions, in the same way that the hexagon was the permutahedron in 2 dimensions, and the segment is the permutahedron in 1 dimension, and this also extends for higher dimensions. So this flat space result is always, or the brain brick model or brain tiling for flat space is always a simple thing, one of these permutahedra. I'm not going to discuss today, but these objects simplify the connection in between gauge theory and geometry. You can go from one to the other in simple ways. There are analogs of perfect matchings, if you want, here that allow you to encode the geometry, and also the story in the opposite direction is simplified. And here it is just a list that replaces, just reiterates all the things I said. Any questions so far? Good. Very good. So Julius is moving, which is a good sign. Yes,
so far, good.
Don't stay still, please, because very good. And with these techniques and before these techniques, we investigated a lot of theories. This is just slice of the many theories that we investigated to give you a flavor of the kind of things that we looked at. We have C4. The toric diagram for C4 is just this tetrahedron in a corner. Very good. So this is a trivial theory to obtain. It's just dimensional reduction of n equals to 4. We have orbifolds, things that look like refinements of that tetrahedron, orbifolds of C4. So like this one here, or like this one. So those are also easy to construct. We have other things that look like 2-dimensional toric diagrams plus a point, right? So this is a Calabi-Yau fourfolds of the form Calabi-Yau 3 times C. So these are truly dimensionally reduced 4-dimensional equals to 1 theory. So these are 2,2 theories with more supersymmetry. These are also easy to get. This one is, for example, the conifold. So you take that, I will say those things. So you obtain it for dimensional reduction. But then we have things which are generally 3-dimensional toric diagrams that are not of this type. We also understand those. The way in which I order this poset or all these theories and the relations is that obviously the toric diagram of one of these guys is embedded in the toric diagram above. So you can imagine that you can also connect these theories by partial resolution. Okay, so for example, this theory looks like the conifold. In green, you have the toric diagram of the conifold. You have an additional point, so this is conifold times C. And the theory can be obtained by dimensional reduction of the conifold theory. Remember the conifold theory in 4 dimensions has two nodes and two chiral fields in each direction. It also has a quartic superpotential. Just if you look at the quiver, each chiral dimensionally reduced to a chiral and a Fermi in two-dimensional 0.2 supersymmetry. So you have these 4 chirals and 4 Fermis between the two nodes, and every vector multiplet reduces to a vector and an adjoint chiral in 2 dimensions. That's what you get. And there's also a prescription to read the interactions, which I'm not going to write here, but it's very straightforward. But we also had things that are completely general. These are, for example, the quiver for this guy, which is called Q111. And this is the quiver for this one, which we call D3. This one in particular the quiver itself looks as if it could be a 2,2 theory, but it is not. The interactions are honestly 0,2. Very good. So what is the summary of this thing? We have tools, we have efficient tools to run this program of mapping gauge theories in 2 dimensions that are obtained on D1 planes probing torical axial fourfolds and the geometry. So you give us the geometry, we can tell you what the gauge theories are, and vice versa. There are other methods. By people in the audience, and also the quivers that we obtain with these methods. In this particular case, we're obtaining some very nice paper by Cyril using the V model and so on. So we can do this. Okay, so but now I'm interested in theories with 0,1 supersymmetry. So let's see how they look like. Okay, so you can write them. Oh, sorry, there's something in the chat. I don't see the chat. Okay. Okay, it was just hide. So you can write them in 0,1 superspace. And once again, you have 3 types of superfields. You have a vector, which on shell it has this left-handed gaugino. Yes, Majorana Weil. You have a scalar multiplet, which has a real scalar. And this right moving Fermi, and you have a Fermi, which has this left moving Fermi. Of course, you see that the guys on shell, you only have supersymmetry for the right movers. The other guys, you will end up without super partners because there's no supersymmetry for the left movers. And there's some superpotential also, the analog of some superpotential interaction, which is a coupling between the Fermis and the chirals. So here there is one such function J for each Fermi, and this function is a real function of the scalars. It's a real function of the scalars. We are going to write theories which are going to be of quiver type. So very much like in the previous slides, I'm going to represent them in this way. By the way, this is not chiral, this is scalar here. So I will have nodes for the vector multiplets. I will have black arrows for the scalars, and I will have red lines for the Fermis. And this is a quiver. Yes.
So in 2 dimensions, I see that you wrote V plus and V minus, right? And 2 dimensions, there is a gauge that you can choose in which one of them is set to 0. So how are you going to treat this?
Right. In 2 dimensions, I will only be left with lambda minus.
Mm-hmm. Right. So you want to set A minus to 0, but keep lambda minus?
Yes.
Does it carry, and it carries 0 degrees of freedom? Or what?
Yes.
Oh, it's,
yes.
So lambda minus should be some chiral fermion, which is massless.
Yes, and it's in the adjoint. Yes.
I see. And then V plus will remain, but again doesn't carry degrees of freedom. Okay.
So the quiver will look, this is just one example of a quiver that we'll construct later. It's just a crazy example that contains as many possible things as you can imagine. There will be gauge groups. There will be some matter fields between them. This is written in 0,1 language. So everything here is like a scalar or a Fermi multiplet. You will see that sometimes you can have unitary gauge groups, and whenever you have unitary gauge groups, everything that is charged under unitary gauge group has to come in pairs, so they can form complex fields. But that's not necessary for the other gauge groups. So this is one theory that was obtained by an Orientifold of a very particular theory, a very particular Orientifold of a very particular theory. We're going to come back to it later. Very good. So one interesting thing is to see, which is useful for our construction, is to see how you take a two-dimensional theory, like a 0,2 theory, and you can write it in 0,1 language. Why? Because we are going to obtain the 0,1 theories as some projection of the 0,2 theories. So, the vector multiplets, the 0,2 vector multiplets can be decomposed in 0,1 vector multiplet and a 0,1 adjoint Fermi. Where typically these Fermis that come from the vector multiplet, we are going to single them out by this superindex R, just to emphasize what are these guys. Then, every chiral multiplet in 0,2 will give rise to two scalar multiplets that they can be combined in a complex scalar multiplet if you want. And every Fermi in 0,2 gives rise to two Fermis. Again, you can combine them into a complex one. And the superpotential here, which is the 0,1 superpotential for a 0,2 theory, has contributions that come from the J and the E terms of the 0,2 theory. And there are also contributions coming from these Fermis in the vector multiplet. So we can write it. So let me just show you an example. This is a this is a quiver for one of the toric diagrams that I will, for a toric Calabi-Yau fourfold that we call it H4. I will give you a toric diagram pretty soon. This is the quiver of one of the toric faces. We also know the J and E terms, but I'm not going to write them here. So everything here is either a 0,2 chiral field or a 0,2 Fermi field. But if you write it in 0,1 language, what you would do is you will take each of these. So now in this quiver, which looks very similar, but it's a 0,1, I will emphasize when something is 0,1. You can also tell for some things, but every black arrow here is a 0,1 scalar. Every line here is a 0,1 Fermi. So everything, the chiral fields are doubled. So here you have an arrow, now you have two arrows, the Fermi fields are doubled, and the adjoint was doubled. No, sorry, the adjoint was doubled, should have been doubled. Right, the adjoint should have been doubled, so don't look at this. And then on top of that, you add one additional adjoint Fermi for every vector multiple. Okay.
Seba?
Yes.
One question. In 0.2, I learned from your previous papers a condition for anomaly cancellation. How that translates to 0.1?
Right. So there's a condition for anomaly cancellation. So this here is an anomaly free. Right. So you can look, the anomalies were very similarly. Then at some point we'll have to deal with this. The anomalies for SO groups and USP groups were very similar with shifts of -2 or +2, when that in the dimensionally reduced theories are in the right place to remain anomaly free.
The question, Seba, is can I have a 0,1 that is healthy, anomaly free, but I cannot lift to 0,2?
Well, perhaps, but those you are not going to see them in this talk.
Okay.
Right,
Okay.
because yes, there are some things which one could, I'm not sure what you're thinking, but there are some questions that one can think about theories that are not going to be of the type that I'm going to discuss today, and whether there are some special features that come from the fact that I obtained them from 0,2.
Okay.
Yeah, that's an interesting thing.
Good.
So regarding the joint on the top left, so how many are in total?
Yeah,
actually?
so it's 6 plus 1.
6 plus 1, so it should be 7.
Yes.
Yeah. Okay. Thank you. Yeah.
Thank you. Thank you. Very good. So very good. So I told you that this is the kind of construction that I want to understand. I added the word Orientifold because we're going to do some Orientifold here, but in principle I have some spin 7 cone, B1 branes, and I want to obtain a theory two dimensional equals to 2 dimension 0,1 supersymmetry. I want to understand the map between the geometry and the gauge theory, at least in some family. And the spin 7 manifolds are 8-dimensional real manifolds in which you can define this 4-form out of the Kähler form and the holomorphic 4-form. Okay. So Joyce realized that there is a nice construction of spin 7 manifolds starting from Calabi-Yau 4-folds, in which if you can quotient by some anti-holomorphic involution, or something that conjugates, if you want, you take your Calabi-Yau 4-fold and you can quotient it by some anti-holomorphic involution I will call sigma, in such a way that omega 4 still remains invariant or well-defined, then the resulting geometry is a spin 7 manifold. Okay, so that's what we are going to try to achieve. We are going to add one ingredient, which is we are also going to quotient by worksheet parity. We are going to construct what we call a spin 7 Orientifold. The reason for this is, initially we really wanted to figure out the geometric counterpart of this observation of the real slicing, and the Orientifold looks like a nice projection of the theory. You can also think that the Orientifold is a projection, but it's a projection after you kind of double the theory. So yeah, that's why we didn't do that. We are thinking about it actually. They're not here, but I think it's fair to say that we were somehow also inspired by an old paper by Forcella and Zaffaroni that use very similar constructions to build n equals to 1 theories in 3 dimensions years ago. So what is the projection? What does the projection look like? So this is, in the geometry there will be some anti-holomorphic involution, some action, which is an involution on the generators of the geometry, which involves conjugation, maybe some signs. But on the gauge theory, it should be a projection by, you should identify one anti-holomorphic involution. Should be a symmetry of both the quiver and the 0,1 superpotential. And if this involution is there, you can quotient by it plus omega. So that's what we do. So the main difference, well, the projections look very similar to the projection that you do when you do Orientifolds. You can have a SO and USP projections. when you have gauge groups which are mapped to themselves, the action on the scalars involves conjugation. That's in order to obtain the anti-holomorphic involution. Here I added something that I will remove later, but there's a possibility when you have several flavors of arrows connecting the same nodes, which are going to be images of each other. There are interesting possibilities of acting non-trivially on those flavors, and those lead to interesting constraints. Okay. And for the Fermis, the Fermis, there are two possibilities of what you do to the 0,2 Fermis, by demanding the invariance of the 0,1 superpotential. You can map them to images up to conjugation or without conjugation. Doesn't matter. That's also related to the fact that what you call the Fermi and what you call the Fermi conjugate to begin with in the 0,2 theory is up to your choice. But for the Fermis, that if you look back at the 0,1 superpotential of the 0,2 theories, for that to be invariant under the involution, the Fermis that come from the vector multiplet have to transform in this simple way without like this. Okay. By the way, they are real to begin with, so there's no conjugation of it. Very good. So again, so nice thing is that, well, it's not a nice thing at this point. Is the statement that you can, this anti-holomorphic involution that underlies Joyce construction is an anti-holomorphic involution on the generators of your geometry, which from the point of view of the gauge theory is some kind of mesons. So you can take this action on the fields of your theory, you can determine the action on the mesons, and you can see what the anti-holomorphic involution in the geometry is, and you can be very explicit about that. There is, so this is general. So, this is the prescription of what you want to achieve. So if I hand you one of these gauge theories, you have to take the quiver, you have to take the J and E terms or the superpotential if you want, and you have to look for all the possible Orientifolds involutions that you can have. And you can have many, you can have none, and so on. There is one that is always there, which is, that's why we call it the universal involution, which is an involution in which every gauge group is mapped to themselves. Then every field is mapped, every matter field is mapped to themselves up to conjugation. And the real Fermis that come from the vector multiplet are also mapped to themselves. Okay, so this thing is always a symmetry and it's always there. It's an interesting involution. I will show you examples of what you obtain by doing that. And this is very trivial, acts very trivial on the generator. It just maps every generator to its conjugate. There's no sign, and there's no mixing of the generators. So let me show you an example. This is the kind of the thing that I was mentioning before, H4. H4 has this toric diagram. It looks like the toric diagram of the conifold plus 2 points on the opposite diagonals, on top of the opposite diagonals. The 0,2, this is one of the toric faces. This theory has more than one toric face. Very good. This is written the Quiver in 0,2 language. We also have the superpotential. We are not writing it for you because for time and space reasons, but we have to take it into account. It's not that we just can look at the Quiver and determine what the Orientifold is. You can look at the Quiver and get an idea of what to try, but of course you always have to check the superpotential. This is written in 0,1 language. Okay, you have everything is double and you get these additional adjoints. And the universal involution is something that maps everything to itself. So you see that that's nice. Once you are in 0,1 language, you can do these things because everything comes in pairs. So you can more or less divide by 2. And every gauge group is mapped to itself. So you can think about it, if you want to think about it in the Quiver, as some plane or reflection plane that is on the surface of the slide. So that's the kind of, it's not a line that connects one half to the other one. In this particular picture, always this universal involution is something that it acts on the plane of the quiver, right? And after your quotient, you get there. This is green for another reason, but this is the quiver that you obtain for a particular choice of sign in the projection. Star means star means symmetric, and rhombus or diamond will mean antisymmetric in the following things. I mean, you have a question?
Yes. How are you computing generators?
Well, the generators, some of us do all the Hilbert series and all this game. Actually, even with RAC, we recently had a paper in which we do it for many of these 0,2 theories. So you can do that. The way I would normally do it is I will construct all the mesons and I will see the relations between them using the perfect matches. And then I would see what the action is.
So, and then do you know that you get all of them?
Right.
You're not missing?
Yeah, we're not missing anyone. Yes.
Okay.
But in the examples that we have worked in detail, we are not missing anyone. Right.
I see.
So we recently had a paper with RAC for all the, which are many more examples that I will going to show today or that we consider for Orientifolds, and for all of them we can do this exercise. We did these things for the 18 regular reflexive polytopes in 3 dimensions. So we did all of that, which are more complicated than this thing.
Yes, I see. And okay, now another question is, so there are many multiplicities, and if one looks only at the quiver, you would imagine that there are many global symmetries, but I suppose that the interactions break most of those global symmetries. Right. So how do you handle global symmetries?
No, we do. No, what we do is we really look at the full gauge theory. I hate, for example, even when we're doing collinear threefolds, but I understand, but I don't like very much when people say, well, you have the quiver, the Orientifold action is this reflection on the quiver, because you really have to take into account the interactions. So here we did take into account the interactions, and there are examples that fail in very subtle ways. Some terms don't work. So that's how we do it.
I see. But an actual computation of the global symmetry by starting from the kinetic terms and then seeing what global symmetries are preserved by the interactions. This sounds like too much work, right?
Well, I don't know if it's too much or too little. I mean, I don't know. I mean, many times I can figure out what the global symmetries are from this thing. And then, I just write the gauge theory in a way that is consistent with these global symmetries. If we want to be more refined, like in the work with RAC, we go through all this machinery of the Hilbert series and so on. We have the generators classified by global symmetries, which beautifully matches the geometry and so on. There are other things that can be done. It's not for the purpose of this talk, but it's interesting. I think it's very interesting is, there are techniques for building these 2-dimensional models corresponding to 3-dimensional toric diagrams out of the brain tilings that corresponded to the 2-dimensional, certain 2-dimensional toric diagrams. You kind of lift it in some way. In those cases, it's very nice to see how some global symmetries might follow from the global symmetries of the brain tiling, how new ones might be generated by the lifting and so on. You can do all these things. There are some beautiful examples of that.
I see. Now, one last question is for toric complex. There is a condition that the rank of the global symmetry is equal to the complex dimension. But once you introduce the spin 7, I guess this is changed. Is there a simple condition?
Right, not that I know, but it sounds like a really nice question. If you are connecting these things to geometries, it's like a nice thing to check. Yes, not that I didn't know.
Okay. Thank you.
Oh, thank you. So now let me give you some other example that doesn't use this universal involution. This is the so-called D3. I show you the Quiver here in 0.2 language. This is the Quiver in 0.1 language. There is one obvious Orientifold. Well, once you have the interactions, but the interactions respect the symmetry that looks like a reflection with respect to this plane. This is the resulting theory. It's complicated. It looks like clutter, but it's clutter because you have two nodes that are going to be identified that have a lot of things hanging between them, and they also have adjoints to begin with. So it's not surprising that you end up with a lot of adjoints, symmetrics, and antisymmetrics, right? So it's just a peculiarity of having all these 8 fields here, plus, like additional 6 fields here. So this is just a peculiarity of this example. This one is another one. Again, I have the same mistake here. I think this is written in 0.1 language, and you can see here a line that is candidate involution. It is an involution, and the question after that. So let me just emphasize a few things of this example for those of you that which are not transparent in this one. Now, for those of you that have done Orientifold before, in the Quiver, for example, you typically map things that have opposite orientations. That's the Orientifold, right? So in this case, the Orientifold also involves conjugation. So the image has the same orientation. Okay, so that's why we also have the universal involution that maps something to itself. You can do that because you have omega, but you also have the conjugation. So this is a nice example in the fact that you have some SO groups corresponds to 1 and 3, but you also have a map between an identification between 2 and 4, which remain unitary. You see that even though we wrote it in 0.1 language, this is a true UN group, so everything comes in pair for it. Has to make sense. While for the other gauge groups, might come in pairs or they might not come in pairs. Actually, typically these things, the pairing is broken by the interactions anyhow, even if they were paired. So, but this is a rather generic example. So now let me talk a little bit about triality. Some number of years ago, now it's quite a few years, Gadier, Gukov, and Putrov proposed a new duality of order 3 for 2-dimensional 0.2 theories. They were constructing the elliptic genus, they're looking at anomalies, and they realized that they had some symmetries. And the main example, or the basic example that you can think about is this one, which you can regard as 2D 0.2 super QCD. So what do I mean here? So you have a gauge group, a unitary gauge group. You have 3 flavor groups that provide the 3 types of flavors that you can have in this case, which are incoming chirals, outgoing chirals, and Fermis. There is an additional singlet of the gauge group by fundamental of the global symmetry group, some meson that you add here, just for the purpose of making the story of the 3 theories more symmetric. If you add this guy, the 3 theories basically look identical. Otherwise, you will have to generate it in the coming steps. In 2 dimensions, there's contribution to the anomaly by the gauge genus. So, once if you fix the flavors, the ranks of the flavor groups, you fix the number of colors. Okay, or if you told me the number of colors and 2 of the number of flavors, you would fix the other number of flavors. So this theory, they propose that it is dual to this one, which is very similar to what cyber duality does. So let's go over that. So in cyber duality, some things happen. First of all, the rank of the gauge group gauge group changes, here the rank of the gauge group changes. It changes in the same way of cyber duality. It changes in the number of incoming chirals minus the number of colors is the new number of colors. That's fine. You know, of course, if I gave you a four-dimensional quiver, you couldn't distinguish between the number of incoming chirals and the number of outgoing chirals, but this is the way in which you can phrase it in this case too. Then in cyber duality, you would say, oh, well, you know, the electric quarks are replaced by the magnetic quarks, which have the opposite charges or the conjugate charges. They're connected to the same flavor symmetries. And you can think about this flipping of the flavors really as a 180 rotation on the four-dimensional quiver, if you want, which exchanges outgoing arrows and incoming arrows. So here the same thing happens. You know, the incoming Fermis become outgoing Fermis, the outgoing Fermis, then the outgoing Fermis become incoming chirals, become outgoing chirals, the outgoing chirals become Fermis, and so on, which can be thought of as 120-degree rotation of the quiver. What I mean by 120-degree rotation is just a rotation of the three types of flavors, just that. And you know, very much like in cyber duality, you can think that a field that is like a meson, a composite field of the original theory, appears as a fundamental field in the dual theory. There's a chiral Fermi meson, which becomes this meson connecting N2 and N3. You can also form a chiral meson connecting N2 and N1, but this theory also had a cubic coupling originally between this Fermi and these chirals that becomes a mass term afterwards, and that's why it's integrated out and removed. You can repeat this process again, and then a third time, and you go back to the original theory. Of course, this example probably hides the non-triviality of the triality because it really looks like a rotation, but you know, it's a very interesting new duality or triality of the two-dimensional 0,2 theory. So a couple of years ago, they realized, or they proposed a similar thing for 0,1 theories. And the theories that are connected by them look very similar. So now this quiver should be thought of as, first of all, these gauge groups are SO. There's a similar version with the USP gauge groups. They look this, but now all these things here are 0,1 fields. There's 0,1 Fermis, 0,1 scalar fields, and there's an additional field here transforming for SO in the symmetric representation. Okay, it's not the adtion of SO. The adtion of SO would be the antisymmetric. Okay, so this is where, you know, these people look at the previous picture, and they say, you know, it really, at least the things that participate in this triality that show up in our calculations look like some quotient, right? We went from, you know, this complex chiral field to X, which is a scalar field, from the complex Fermis to the 0,1 Fermis, and so on. Very good. So this was a comment about the slicing. Do I have 5 more minutes?
Yeah, sure. I think it's good.
So what we want to say, you imagine, is that the map between spin 7 manifolds and gauge theories is not one-to-one. It's typically one-to-many, and that whenever there's non-uniqueness, that non-uniqueness is related to this new triality. Okay, and furthermore, if you look at this basic example, one would say that they are related by precisely the universal involution. So you took the previous quiver, the 0,2 quiver for super QCD, you did this basic involution that always works, and it will produce this. By the way, it was not so easy to provide quiver examples, more general quiver examples for this triality, 0,1 triality. Gukov, Pei, and Putrov very briefly discuss a very simple family of quivers. It's a very simple family of quivers in which you take basic elements that look like building blocks that look like this quiver, and then you gauge some of the flavor symmetries, and you identify them with the nodes of the other quivers, okay, with the gauge of the other quivers. Why do I say that it's a very simple version? Because once you do that, you preserve the local structure of every. Well, that one of the reasons is you preserve the local structure of each of these building blocks. So what reality means in each case is very clear. However, if I show you this quiver, which now is completely unoriented, has no arrows, right? If you have a more general version of it, you could ask, for example, how I make, which mesons I'm allowed to make and which mesons I'm not allowed to make. Right, so why do I make the Y side meson but not the X side mesons or things like that? Okay, or why do you do the X side? This is the one that is made, but I don't do the Y side. So what we will see is that once you construct these triality dual theories by obtaining them by these spin-stable Orientifolds, these ambiguities will be explained because they will be have an origin in the original 0,2. Okay. So, Ami, yes?
Yes, so was there any attempt to put this in the context of cluster algebras, so to relate this to reality?
Well, yeah, well, I have been pushing for a long time to put this one in the context of cluster algebra. I mean, this one and there is a similar version for graded quivers for higher end. So this would be the m equals to 2 case. There are many others. So I think they are very, very, very natural field theory operations because people have thought about generalizations of cluster algebras, which to me look pretty ad hoc. This one is really well motivated by a concrete duality in gauge theory. Even the quivers that you think about are very natural. I think that this is the type of quivers that you have to look at in order to think about the generalization. You can go, and I have talked to Lauren Williams, to Musiker, to Kenyon, and things like that. We have a grant together, so I keep coming back to this. I think this is a thing that needs to be done.
There
is one part that is not very clear. So of course, the quiver transformation, you know it. Even if you want to consider with superpotential, you know it. The coefficient transformation, you also know it. And then the analog of the exchange algebra, there are some things that you can propose. And whether they satisfy you or not, that's the issue. So at this point, we don't have it. It's something that we are working on. There's no obvious thing that stands out. Of course, another thing that matters, I think, to me is that the cluster algebras, once you have it, you recognize that they describe many other systems. So you would also, once you have one of those proposals, you will have to find some other things to which they apply, which we can get some of them, but yeah. So the answer is that I fully agree with you that this is something that is very natural to ask, and I have been trying, and I keep trying. There's one of the ingredients that is missing.
I see. So did Anna look at this? And Ralph?
Maybe we can do this after the talk.
Yes.
Maybe let's do it.
Yes, and you delete the record. Yes. You put the P, so we don't. Very good. So let me talk about, just have 2 slides and the conclusion. So let me talk about triality and the universal involution. I told you about H4. H4, here I'm showing 2 phases for H4. It's 0,2 theory is related by 0,2 triality on node 2. Right? So this, you can think about these theories as resulting from the non-uniqueness of the geometry to gauge theory map. So you go, you try to calculate the phases of this thing, you obtain these two theories, or you can think that you obtain one of them and you apply triality locally to this node. So they're the same thing. So this is what I would call a geometric perspective on triality, if you want. You can do this universal involution of each of them. Right? And maybe this series is fine. And you have to think a little bit more about that thing. You can do the universal involution on the other one, and you obtain two theories. So you started from two theories, from the Calabi-Yau fourfold. You did the universal involution, you did triality, they were connected, furthermore, they were connected by 0.2 triality. Each of them can be Orientifolded by this universal using this universal involution. You obtain these two theories. Now you look at them, and they are related also by the 0.1 triality on the node that you were considering. This is not a big surprise because really, the universal involution acts by projecting the original 0.2 triality to 0.1 triality. And of course, if you look at the two-gauge theories, you look at how you map things, and you look at what you did to the generators, you can indeed confirm that you are doing the same Orientifold in both cases, right? Because it wouldn't be a dual if I was doing some other Orientifold. Let me give you an example that goes beyond that universal involution. This is the QN1 mod C2, has this toric diagram, which is like this three-dimensional version of F0, which is very nice. This theory has a very rich space of toric phases. It has 14 toric phases. If you computed the 0.2 theories for each of them, and Asim, I think Asim was there, Asim classified them, you will obtain these 14 theories. Let me take one of them, which is what I call phase T. This is, you can see here how complicated this thing is. So this is a quiver with 8 gauge groups, 24 Fermis. For each of the 24 Fermis here, you have all the J and E terms. We know them. And of course, I drew the quiver in a special way to make some involution manifest, right? I want to, and this has 27 generators that we found, we express it in terms of the gauge theory, the geometry, and everything, right? So I would like to consider an involution that maps the left side to the right side. That's why I drew it this way. Of course, the symmetry is there regardless of how I draw the quiver, but I want to make it explicit. So now you can look at the 14 toric phases and find which of them, determine which of them admit the same involution, right? Because some of them might not. It's like when you have even in 4 dimensions, when you have a brain tiling and you have some Orientifold and then you do some cyber duality that doesn't respect the symmetry of the Orientifold, that other guy won't exhibit the same involution. It's not permitted there. So, by the way, wait. If you do the quotient, you obtain this thing. So there are 4 nodes which are on the plane, become these SO nodes, and there are 2 pairs of nodes that are mapped to each other that give rise to these 2 unitary gauge groups. So, very good. So these are the 0.2 theories. I told you that there are 14, but the 5 that admit, there are 5 of them that admit the same involution, which are shown here. And it's interesting that they're even connected by another one, which doesn't preserve involution. So you can imagine that this is a cyber duality on a node that is not on that plane. It broke the symmetry, then you do another duality, and you come back to something that is symmetric, and you can do the involution. And here the arrows are colored in a beautiful way to indicate which node are you dualizing to go from one to the other. Okay? So now you can take these 5 theories, this web of dual theories, 0.2 dual theories, and you can Orientifold them by using the same involution. Right? When I say using the same involution, I mean 2 things. Either it's something that looks the same in the quiver, but even that when you look at the level of the generators, it's the same action on the generators. You can verify that. And again, in all these cases, what I do is I verify that the involution is the symmetry of this order 20 sets of interactions. Okay, so we check all this. And you obtain this thing, which is, it's a nice, this are the Orientifold theories. It's very nice that some of them are connected by 0,1 trialities, right, on these SO nodes with 0,1 matter and so on. Some of them locally are related by the dualities on the unitary gauge groups, which you can think about them as the 0,2 triality. So I think that something nice that comes out of this construction is that you can regard these theories as consisting of 0,2 and 0,1 and 0,2 sectors. There are 0,1 theories overall, but they have 0,1 and 0,2 sectors. You have dualities that act on the different sectors. So you can think that there's 0,2 triality, which turns out to be a 0,1 triality because the theory was coupled to a 0,1 sector, so you only have 0,1 supersymmetry. Maybe the interactions brought them to 0,1 and so on. So in some sense, it provides a generalization and a interpolation between 0,1 and 0,2 cases. So conclusions. So we started.
But before can you go back to the lattice of generators? So I wanted to ask, what is the status of reflexive duality? Because I see
what
there's
is the
one.
status of reflexive duality? Yeah, I'm not sure. Yes. So so what do you mean?
So you see that in this lattice that you draw, there is only one internal point.
Yes. So
the corresponding, if you think of it as a toric diagram.
Right. So if the question is, can I take all the reflexive polytopes, construct the polar duals which are also reflexive polytopes, and build phases, gauge theories for all of them and call them reflexive duals? Hasn't been done because there are 4,300 of them.
Yeah, there are thousands. Okay, 4,000. Yes. Okay.
Right. Yeah. Then if you look at the regular reflexive ones, there are 18 of them. We built all of them, but once you consider the polar dual, you are in this non-regular case.
Right.
So, right. So
yeah, you get 18, which are as full of singularities as can be, right?
Right. And there's some of them they're beautiful shapes. Some of these things are beautiful. You can see, in this, you can slice. You see that there are SU2 times SU2 representations here because this has SU2 cube. There's a beautiful structure in all these things. Even in more complicated things, you have this beautiful structure. I think it should be investigated, probably with a computer. I don't know.
Right. I see. And I guess you could also come up with some rules for some magic numbers, like.
Right. That's one thing that we did, for example. Actually, I think we did it with Cyril and Nassim. There are also other interesting directions for getting interesting numbers that you can think of, right? So one of the things that we did, I told you that I didn't go into this, but there are ways in which to build theories for toric diagrams that look like the lower dimensional toric diagram lifted in a specific way. So you can think that this toric diagram was F0 lifted in a special way. The middle was lifted in that way. And furthermore, that F0 was, C2 mod C2 lifted in a special way, right? Well, doing that, what we did is we actually added a new direction to these infinite families of toric things that we can build. There's another analogy of plane tilings and so on, but we had another axis which goes in the dimension, right, of the Calabi-Yau manifold. So even without going into these 4,000 complicated things, one thing that one can do, for example, is looking at this, the cute ones, like this SU2 times SU2 times SU2 symmetric object, and build toric quivers for all of them. Right? And there are beautiful numbers, beautiful things of perfect matches, and so on. So there are many many nice mathematical things and geometric things to investigate.
Yeah, but even things like, in torque diagrams of dimension 2, you have that the reflexive dual has a number of gauge loops, and the sum is always 12.
Right.
So things like that, some kind of a conservation laws.
Right. It would be very nice to investigate. Maybe with not the 4,000, but with a few of them, we can figure it out.
Okay.
Right.
Thank you.
So we started this engineering of the 0,1 theories using spin 7 manifolds. The real slice, the nice thing, I think one of the nice things is that we connected this real slicing to the anti-holomorphic involution in choice construction. Right. So if we want this thing that probably was natural if you want to go from 0,2 to 0,1, but that you didn't have much of additional support. Here we really connected to this geometric operation. I didn't discuss things like partial resolution of these spin 7 cones or the choice of vector structure, which was something interesting when we try to identify duals. Spin 7 Orientifolds provide a geometric perspective on 0,1 triality, which is, it depends how satisfying you find it, but it comes from the fact that multiple theories correspond to the same Orientifold. And I think that the generic case, you can call it a generalization of the basic triality in the sense that they interpolate between pure 0,2 and pure 0,1 triality. As always, every time you have new tools or new perspectives, I expect that they will lead to interesting things that we can investigate, and that's everything. So thank you.
All right, let's thank Seba. And before he gets to the additional slides, do we have any questions? So if we don't have any questions right now, then I'd say let's thank Seba again, and then continue with some cluster algebras.
No, maybe.